shows up. All right, so here we go. So I guess last question. Go ahead, Joe. Unfortunately, I don't have any spare copies with me right now. But as I've said, all the handouts are posted on the web. So maybe you can download that and take any extra notes right now. All right, so very quickly, what we were doing last time was we had started this topic on calculus of scalars, vectors, and tensor fields. Okay, and last time we were basically discussing scalar fields. So I pointed out what scalar fields look like in 2D and 3D. And we also set up something called a directional derivative, because in 2D and 3D, the direction in which you take the derivative matters. Right? We saw that in some directions, the rate of increase of your function might be the maximum. In some directions, the opposite direction would be the minimum. And perpendicular to that, the direct rate of increase of that function might be 0. So that was the directional derivative. We also looked at another derivative which is called the gradient of a scalar field. And again, looking at the same scalar field x dot x, we found that the gradient of this scalar field came out to be a vector field, which basically says that if I have a scalar field over the space, a 2D space or a 3D space, go to some point and plot the magnitude and direction of the greatest increase of the function at that point. So magnitude and direction of greatest increase would be a vector at each point. So that's what makes it a vector field. And we looked at this example of this function which gave you this particular vector field. 2x was the vector field corresponding to the scalar gradient of that scalar field x dot x. So we saw, of course, no change in function at 0, at the 0, 0 location. And as you go radially outward, the vector field associated with that gradient also grows as you go more and more out, and it obviously points in the greatest increase of that function, which is also radial. So maybe I'll take a very quick example here. So let's set up a scalar field of a vector variable. Anybody want to give me an example of a scalar field of multiple variables, 2 or 3 variables? Say again. X, Y, Z. Okay. So that I will write it as x1, x2, x3. Right? That's x, y, z. The gradient of that scalar field shouldn't be marked as a tensor, but a vector. So gradient of that vector field of x, and actually again here, this equal to is fine because it's a scalar on both sides. Here I'll mark it as can be represented by, and one easy way to do that is to take partials of this function with all 3, and of course that turns out to be equal to x2, x3, x1, x3, and x1, x2. Right? Now I'm not visualizing this this scalar field, but you can sort of think about what this might look like on all the 3 axes, E1, E2, E3 axes. On all the 3 axes, the value of that scalar field would be 0. And as you're kind of going out of the origin, the value of that scalar would increase between those axes. So, each, if you were to associate this vector, this is a vector, so you could go to each location in the space and mark that value or mark that vector at that point. Again, that would look something like a bunch of arrows over the entire space, and the magnitude of those arrows would also be growing as you go out. Right? So this is a simple example of what a gradient of a scalar field would look like. So you could set up your own scalar fields, take gradients, and try to think about them, visualize them in your mind, or even use MATLAB to plot them. Okay. All right. So let's go back, and very quickly I'll also mention what we did last time was that we looked at a definition that did not rely upon. So right now in the example that we looked at, we relied on this definition: partial of f with x1, x2, x3 in the corresponding E1, E2, E3 directions. But last time we also set up a definition of the gradient which does not rely upon a coordinate system x1, x2, x3 or even E2, E3. We said that we'll follow the same definition that we did for the 1D case. Flux of the function f over the boundary of a body. In 3D, this was the boundary. In 3D, this cube was the body that we chose. And in 2D, this rectangle was the body that we chose. Flux over the boundary of the body divided by the measure of that body. That works in 2D and 3D. Exact same definition works both of these in those cases. And I showed you that for a particular example, when you are looking at a cuboid type object body, you can go through the algebra, calculate the flux of any function, over the surface of that body, and divide it by the volume of that body, and you come up with the component definition of the gradient that we had seen earlier. Okay. All right. Any questions about the gradient or the directional derivative of scalar fields? Okay, so let's switch to vector fields. What are vector fields? Any examples of vector fields that you might have seen before? Velocity of a deformable body or a structure. In fact, this building that we are sitting in right now has some small ambient vibrations going on. Each point in the building is oscillating or vibrating a little bit, and the instantaneous velocity of each and every point gives you a bunch of arrows for this entire building, right? That's what a vector field looks like, a bunch of arrows. So for example, if I look at this vector field, this is a vector field because it is a vector function of a vector of the position vector. It takes x2, x3 in the E1 direction, x1 plus x3 in the E2, and x1 plus x2 in the E3 direction. So if you were to plot that over a unit cube, this is actually not a unit cube, -2 to +2 in all the three x1, x2, x3 directions, that would look like this. It has a bunch of arrows associated with each point in space. That's what a vector field looks like. In this particular case, you can see that when you're at the origin, the value of that vector is 0, right? And as you go away from the origin, you can kind of see that this could be like a flow within some object. So you have flow going from this direction in the top face, in this direction, on the left face, and on the bottom face in all these different directions. This is a velocity field or a vector field, or an example of a vector field. And again, we will represent it with these three components in the E1, E2, E3 direction. So that's what basically a vector field looks like. Let's see what kind of derivatives we can work with for a vector field. For a scalar field, we had two derivatives, a directional derivative and a gradient. Here we are going to introduce another derivative which is called divergence of a vector field. And what it measures is the amount of flux of that vector field or the rate of change of flux of that vector field at a particular point, basically how much material is coming in and how much material is going out. If you are at a point in that vector field, maybe some point out here, then you can kind of surround that point with an arbitrary body, um, and you can measure how much material is coming in due to this vector field, how much material or flux, essentially how much flux is coming in and going out. The amount of flux going out minus the amount of flux coming in as the size of this body tends to zero is what divergence is. So it's you're measuring rate of change of flux in the neighborhood of a point. And the way it is defined, again, is very similar to the other definitions of our derivatives in 2D and 3D. We will, since we have a vector field now, we are going to measure flux with V dot product with N. N is the normal vector at that point. We are going to, the dot product, of course, would be a scalar. And we take d over the boundary of that body, or the boundary of that body would be a surface. So I'll do a double integral purposely there, and I'll write area of the body and divided by 1 over volume of the body, and all of that in the limit that volume tends to 0. So volume of body tending to 0. Again, what I'm talking about is, say at this point, or at any point x in the field, you go to point, imagine a small body, infinitesimal body there. You can measure the flux incoming and flux outgoing of that body. And the normal vector that I'm talking about here is the normal vector, for example, at any point in that surface, that's n. So you would do that integral all over the surface of that arbitrary sized body. You can calculate the volume and the surface area of that body as well. And then just plug that into this definition, and you would have something called the divergence, the rate of change of flux at a point. Now, there's a much more convenient way to calculate that using components. And in components, a divergence of a vector field gives me what? Does it give me a scalar, a vector, or a tensor? What is the dot product of V dot n? Scalar. Integral of a scalar over a surface, scalar, divided by the volume, again a scalar. Right? So the result of all of that is a scalar. Gradient of a scalar field gave me a vector field. Divergence of a vector field gives me back a scalar field. Okay, and the way that we will define in components would be, just take the v1, v2, v3 components of that vector field and take partial derivatives with respect to x1, x2, x3, and just add them up. And indeed, that would be the divergence of that field. You can show in a very similar construction, you can show this. And if you were to follow the initial notation, you would write partial vi, partial xi. What does that mean? Partial vi, partial xi? What is partial vi with respect to partial xi? If I were to expand it out, it would be right there, right? I is repeated, so I means goes from 1 to 3. So all we are doing is calculating for I1, I2, I3 and summing up the result. That's indeed what we are going with the initial notation, partial vi, partial xi, as a function of the vector x. And as one another quirk of this initial notation, um, people did not want to write all of this partial with partial xi kind of, and they started denoting that with a comma. So when I write vi comma I, that comma I denotes partial with respect to xi. Okay. So talk about being lazy, right? We didn't want to write summations, so we said that I and I, whenever they're repeated, we'll assume that there is a sum. We didn't want to write partials, so we said comma I will denote that partial. So, but anyway, this is just notation, okay? And another way to, or another easy way to remember this is that if you're given a vector field, just take a dot product of that vector field with the grad operator. This is called the grad operator. The grad operator is nothing but partial with respect to x1, partial with x2, partial with x3. Okay, and I'll show you in a little bit later. I don't know if you can see the green comments below. Since it's a dot product, grad of v is the same as v dot grad. Now I'll make a quick comment here. V dot grad means something like this. So maybe you can take this example and that will be more clear. Let's take this first one. The same vector field that I had on the previous page, right? X1, x1 plus x2 in the x3 in the E1 direction and so on. If I were to do the directional derivative, or I have that x2 plus x3 E1 plus x1 plus x3 in E2 plus x2 plus x3, no, x1 plus x2 in the E3 direction. So that's my vector field. And if I want to take, I can represent this again as x2 plus x3, x1 plus x3, and x1 plus x2. And when I said that divergence of v is equal to, grad dot v, what we're talking about is take the partial with x1, partial with x2, partial with x3, and operate it upon this vector field. So, okay. Oops. Okay. It's going to make me write out, but all right. So x2 plus x3, x1 plus x3, x1 plus x2. And if I do that, what's the result? Right? The first one does not depend upon x1. The second one does not depend upon x2. The third one doesn't depend upon x3. So the result is indeed 0, 0, 0. And in this case, that is just equal to the zero scalar, no vector sign under, sorry, you're right. It should be zero scalar, not a zero vector. Okay. So dot product is taking the dot product of this guy with this guy. Now, as I said, another way to think about this is to write v dot grad. That's the comment under the definition that you have on your handout. What that means is that all I'm doing is changing the order of computation of x2 plus x3, x1 plus x3, and x1 plus x2 with respect to partial 1, partial x2, partial x3. Now you might think that when I take this dot product, what do I do with this partial on the right hand side? But the way to interpret that again is that when there is a partial, even on the right hand side, we are still going to take partial x1 of x2 plus x3. Okay, so even when I write v dot grad, we are still taking partial derivatives on the left. Okay, and the reason why I'm writing it like this will be clear very shortly, because there are other types of derivatives for vectors and tensors that work much more nicely when written in this manner rather than this manner. Okay, so that was the first example. Let's take a minute and do the other two examples. So I'll let you work on those first, and then we'll do them together. The first one or the second one is the vector field x. What does the vector field x look like? Before you jump into that example, what does the vector field? It is a position vector, but have you seen the vector field x? Have I shown you the vector field x? Have I shown you the vector field 2x? Take a look at your notes. No, that was a, all right. This was the scalar field x dot x, okay, which was x1, x1 plus x2, x2 plus x3, x3. This was the vector field 2x. What would a vector field x look like? Exactly the same, but arrows would be half the size everywhere, right? So that's the vector field that we're talking about in this second example. What do you think would be the divergence of that? Why is that? So what does divergence measure? Divergence measures the amount of outflow minus the amount of inflow at a point. In that particular x field, when you're at any point, the arrows pointing outward, are they bigger, or arrows pointing inward, are they bigger? Arrows pointing. So if I'm at a point, arrows pointing slightly outward, slightly bigger than the arrows pointing inward. So we would expect the divergence of this to be positive. Yeah, positive. But let's see, what would that be? So the first one we've already done, that is 0. The second one, the third one is what I want you to do, and tell me what you get. Go ahead.
This operator also means
Nabla. Yeah, that's a LaTeX version, but yeah, sometimes they call it Nabla. But it's a partial derivative. All right, second one. That's not so difficult. 3, right? Take the first component, partial with x1. That gives me immediately 1. Second component, partial with x2. That's also 1. Partial with x3. That's also 1. 1 plus 1 plus 1. That's indeed 3. And maybe just to make it explicit, I would write that as delta I. Why would it be delta I? We have partial of, so the vector field itself was x, and I'm writing divergence of x. So that's partial of xi ei, right? This is my vector field, and I'm going to take partial with respect to j, and I'm going to take the dot with ej. Does that make sense? Isn't this what dot product is? Take the vector field, dot it with the, maybe, okay, I'll write it like this. Does that help you visualize that? We have the vector field v, that was my vector field v, and all of this was the partial or the grad operator. So I'll call that the grad operator, and we have a dot product between them. Right? Xi ei is the vector x. This is this is also a vector. Any vector v, I can write it as vj ej, right? That's what I'm doing here. So if I expand it out, I get partial of xi partial of xj times ei dot ej. Ei dot ej I know is delta ij. And what is partial of xi with partial of xj? Also delta ij, right? This is also, if it is partial of x1 with respect to x1, we get 1. x1 with x2 or x1 with x3 is 0. So indeed, that is also delta ij. What is delta ij times delta ij? Delta I, because you could, or delta jj, depending upon what you contract. I could contract out j here, replace that with I get delta II, which indeed is 3. So this was maybe the initial way of going about it. Alternatively, we could do exactly what I did in words a moment ago, just taking partial derivatives. You would have still gotten the same thing, 3. How about the next one? Partial of this with respect to x1, 2x1, this will be 2x2, this will be 2x3. Can I write that as 2xi?
No, summation.
Right, I would have to have the summation there because I is not repeated. So I would write that as 2 of x1 plus x2 plus x3. And question? Okay. Or I could write that explicitly as 2 times summation of I equal to 1 to 3 of xi. The summation sign is necessary there because I is not repeated.
So you can write 2xi.
Okay, good question. Can I write that as 2xi ei? We cannot do that because this 2xi ei is a vector, right? And yes, it would imply x1 in the e1 direction plus x2 in the e2 and so on. So that is not equal to 2x1 plus 2x2 plus 2x3. All right. Any questions on this? Okay. All right. So going on with the types of derivatives, we have yet another type of derivative for a vector field called a curl. How many of you, by the way, heard of these divergence, curl, and gradient? Or calculated it maybe long time ago in your multivariate calculus class. This is indeed the exact same thing, just written in our notation. So curl is defined as just like divergence kind of measures the amount of flux outgoing minus the amount of flux incoming, curl measures the amount of circulation around a point. So if I go back to this picture, this was my vector field that I was talking about. Again, if I want to measure a curl of this vector field, I would go to that point, surround myself in a small infinitesimal body, and try to measure how much of that vector field is circulating around that point. How do I measure circulation? That's done through a cross product. So what we will define that is again with a vector field x as a position as a function of position, cross product with the normal vector at any point on the surface of that body. The cross product would give me a vector, correct? I would take that vector and I would integrate that over the surface of that body. So I'll have that again area of that body B and divided by the volume of that body. That's again the same definition as the derivative and indeed in the limit of the volume of that body tending to 0. So as I shrink that body down, I'm measuring what is the amount of circulation around that point. Kind of hard to visualize, but this is a type of derivative of vector fields. In components, once again, this is not too difficult to calculate. We have these two these expressions for the curl. where we'll take the cross product of the given vector field with the gradient operator. The gradient operator, as I said, is just del x1, del x2, del x3. Take the cross product of that, and in a slight difference from notation from your books, I have a negative sign here. So there is not a complete agreement even among the authors here. What is curl? Is it negative grad dot v or is it positive grad dot v? Some people say it's negative, some say it's positive. But just to be consistent with the notation that we are talking about in the green below this box, the curl can again be written as v cross with grad. So if I have two vectors, so if this is my grad, and if I have a vector field v, I will do v cross grad. Cross product will give me a vector. So if I switch the order, then I would have to have a negative sign here. I think in your textbooks, this negative sign is not there. So this is a difference in convention. The underlying quantity, the cross product still remains unchanged. Okay. So I don't have to tell you how to do this cross product. You can do exactly using your matrix operations. All you have to do is to set up the gradient vector and take a cross product with the vector field, which we'll do in a little bit. Let's take a look at this. V, the vector field V equal to X, we know what that looks like, arrows pointing outwards. First question, intuitively, what should be the curl of this vector field X that points radially outwards? 0. Right, because if you go to any point, there's no circulation of that vector field around that point. So that should turn out to be the case. Let's see. We'll take minus partial x j ej. All I did was write the gradient operator, right? Minus of partial xj ej, and cross with x xk ek. And since we know that the cross product of two vectors can be written in terms of the alternating symbol, the epsilon ijk, we can write all of this as epsilon ijk xi comma k comma j and ek. So let's first take a minute here and make sure we understand what this is. Where did I get epsilon ijk from? Because we are doing a cross product, right? Epsilon j cross I and negative of that would be epsilon ijk ek. The derivative vi comma j is nothing but the derivative of the vector field I component with the j component, straight away from the definition. In my current case, the vector field is just xi ei. So the derivative of v, since vi is equal to xi, in my current case, it is just xi comma j. What is xi comma j? Partial derivative of xi with respect to xj. And what is that? It's not 0, it's the delta ij, because when I and j are 1 and 1, I'm taking derivative of x1 with respect to x1. When I and j are 1 and 2 or 1 and 3, the derivative is 0. So indeed, partial, this guy is delta ij. I can again contract out j with, let's say, j here in the epsilon. I have epsilon iik. What is that? 0. Any two indices of epsilon, when they are same, we get 0, right? So no surprise there. It's the 0 vector. Okay. Curl of the vector field x gives me, where did my vector sign go? Gives me a 0 vector. Okay. Questions? All right, so let's do this example by yourself. I've already set it up for you. If I have a vector field which is slightly different from the one that we were just talking about, x2 minus x3, x3 minus x1, and x1 minus x3, if we want to do the curl of this vector field, you would do it in the same way that you calculate cross products, right? Top I have even e2, e3, I have v on the second row, and I have cross gradient operator on the third row. So if you do that, what do you get? All right, maybe you should do it together since this can take some time. Um, so E1 times this minus this times that, right? So we'll have E1 and um, partial with respect to x3 of x3 minus x1. What is that?
1.
Okay. So I have 1 here. And minus of partial with respect to x2 of this guy. So x1 minus x2 partial with respect to x2 would give me minus 1. Minus of minus 1 would give me plus 1. Right? Minus e2 times, so again I'll do partial with x3 of this one. That's minus 1. And minus partial with respect to x1 of this x1, so that's again a minus 1. And finally plus e3 times, no surprise there, we would have partial of x2 with respect to x2, that's 1, and minus of minus 1, that gives me again a plus 1. So the result is 2 E1 plus 2 E2 plus 2 E3. Okay. Question? So all we are doing here is just taking partial derivatives and trying to understand how to do that for these different types of derivatives. So we did divergence, we did curl, and similar to the scalar fields, we have gradient of a vector field again. Okay, so what does a gradient of a vector field measure? It actually it results in a tensor field. So first was a divergence of a vector field that gave me a scalar field. Second, we looked at curl of a vector field that gave me a vector field. Now we have a gradient of a vector field that will give me a tensor field. And I'll talk about what a tensor field actually looks like. But what does this measure? It measures how a given vector field changes in all possible directions. Okay, so if you think of let's say this vector field, the vector field 2x or x, if you go to a particular point, you can imagine that the vector field at that point could be varying. If I move in one direction, I have one rate of change. If I move in another direction, I have yet another rate of change, and infinitely many possible rates of change in all these infinite directions. Correct? What the gradient of a vector field captures is what is the rate of change in all possible directions around a particular point. And as you might think, that will look like an ellipsoid, because if you go to a point, you point me in any particular direction, that would be one of the possible directions of that red sphere going to a blue ellipsoid. Okay, so each point, you could go to any point in here and try to figure out what would be the rate of change of the vector field in the neighborhood of that point, and that would look like an ellipsoid, and that's what this gradient captures. So to do that, we would have to do Vx tensor or dyad product with the unit normal on the neighborhood of that surface, that dyad immediately is a tensor. Integrate that tensor over the area of the surface on the boundary of that body, area of the body B, over the volume of that body B. Take that limit of the volume tending to 0, and that is the definition uh, of a gradient. In terms of components, it's much easier to calculate. You could take V dyad with grad. What does that mean? Just like a dot product, you take a horizontal vector of gradient, dot product it with the given vector field. In this case, we will take the outer product of, of the gradient operator. So if I have a vector field VI EI, the dyad will do partial of VI, partial of XJ, EI dyad EJ. So you remember EI dyad EJ, what is EI dyad EJ? It's a tensor, actually 9 possible tensors, depending upon the values of I and J, right? So EI dyad EJ gives me the 9 possible components of this resulting tensor. Each one of those components is nothing but partial VI with respect to EJ. So V1 with respect to V1, V1 with respect to V2, and so on. That's what a gradient of a vector field does. So let's take a look at this guy. We have V, if it is equal to X, the vector field X, what would the gradient of that vector field be? And note that I'm writing the result gradient with a tilde because it's a tensor. We can calculate that as partial xi partial xj ei dyad ej. Do you agree? Why is this gradient of this vector field x equal to partial xi partial xj? What is the ith component of this? So x can be written as xi ei, right? And if you look at this components of this matrix, all we are doing is take the ith component, derivative with the jth component, and that will fill out the 9 components of this matrix. So what is this? Delta I, delta xi, delta xj? Again, delta ij, yes. This is nothing but delta ij. And at this stage, you could directly write this as what? This is the identity matrix, or the identity tensor, I should say. This is the identity tensor field, actually. So in reality, what I should write is this, because at each point x in the domain, I have an identity tensor associated with it. And of course, if you want to look at it explicitly, you could again contract out j and replace that with I. So what you get here is EI dyad with EI. EI dyad with EI is what? EI dyad with EI. It is identity. It's E1 dyad E1 plus E2 dyad E2 plus E3 dyad E3, which is what? 1, 1, 1 on the diagonals, right? That is indeed the identity tensor. What is the physical meaning of this? We had this vector field that we were talking about. This is the vector field 2x. X is very similar. For this vector field, I'm saying that the gradient which measures the rate of change in all possible directions of the vector field is identity. So what we are saying is that you go to any point in space in this vector field, go to any point in space, and you have an identity tensor associated as the gradient of this vector field, which means that identity. What does an identity tensor look like? That's a component visualization, but what does a tensor look like? It looks like ellipsoids or spheres, right? Identity tensor looks like a sphere. So what that says is that if you go to any point in the space of this vector field, the gradient of that vector field looks like an identity tensor, which is a sphere in all, um, which measures the rate of change of that vector field in all possible directions. So, um, um, so, uh, so basically, we have covered these three types of derivatives for the vector field. Go ahead, Kajwin.
Yeah, and I think there have another expression for this, the left gradient or right gradient.
That's true.
So you
So yeah, in some books you'll see sometimes there is a left derivative versus a right derivative, or a left gradient versus right gradient. We are not distinguishing with them right now.
but in this problem, the left gradient have a different value to the right gradient of a vector field. Of course, if it is not a symmetric, if the result is not a symmetric tensor field, then the left gradient and the right gradient will be different.
That's true.
So maybe we are using the right gradient for the most case.
I think since since we are not distinguishing between the left and the right gradients, the gradients of these vector fields will usually, or the ones that we will work with, will be symmetric, because this will result in a tensor field. Or usually what we'll work with when we take gradients of changes in lengths, we'll get strains, or when we take gradients of fractions, we'll get stress tensors. So in both of those cases, the results will be symmetric tensors. So yes, that's why we are not distinguishing between left and right gradients. But again, that's something that is not needed in our case, as you're right. Left and right gradients usually do result in different tensors. But okay, I think we have run out of time here as well. There is example 7 in your book that will also help you understand some of these derivatives for the vector fields. So we'll stop here and we'll come back and finish out derivatives of tensor fields and some integral theorems next time. I think for the homework 3, there is one problem which requires you to work with derivatives of the tensor field, which I didn't quite get to. Maybe what we'll do is, give it a shot. See if you can read the book and understand the material and solve the problem. If not, we'll have to maybe extend the deadline or do something like that. All right, so I'll see you all on Wednesday.